Welcome to the 22nd lecture of graph theory. In the last class we had discussed the coloring of digraphs. We were talking about a theorem called Gallai-Roy theorem, which says every digraph D contains a directed path with chi vertices, chi being the chromatic number. See, the chromatic number of a directed graph is not different from the chromatic number of the underlying undirected graph. So, it is just that whenever we give colors to the vertices, we have to make sure that two adjacent vertices get different colors. So, here it is a directed edge rather than a undirected edge, that is all. So, it is natural to see whether the statement is valid in the undirected case. So, which we can easily verify as follows. How do we do that? So, we know that there is a critical subgraph of the given graph, color critical. If it is a k chromatic graph, then the k color critical subgraph is available. So, how do we do that? We keep deleting vertices and edges until it becomes critical, right. That means deletion of any more vertex or edge from the current graph will reduce the chromatic number from k to something else, k to k minus 1. So, such a structure, we know the critical graph has the following property, namely its minimum degree is k minus 1. This we had seen in the last class. So, now if the minimum degree of a graph is k minus 1, we know that there exists a path of length or path of k vertices, path having k vertices in the graph. How do we know that? It is just we take the longest path, and because the end points of the longest path should be such that the neighbors of all the neighbors of this end point should be in the path. So, k minus 1 neighbors plus that vertex itself will make it k. So, the longest path will be having at least k vertices in it. So, this we had seen in earlier classes, that minimum degree implies that there exists a long path of. So, then if the graph chromatic number is chi, then definitely there should be a path of length chi. Now, the question is, when it comes to the directed graphs, does it hold good even after giving directions? That means you are given an undirected graph. We know that there are some paths of length chi here in this undirected case. Then now we are allowed to give direction to the edges. Is it? But we can always give. We can try to give directions to the edges in such a way that each path of length chi becomes. I mean, the directions are not correct in that path, right. It becomes, it will not be an directed path, though in the undirected graph it is a path. So, is it possible to direct the edges like that? Gallai-Roy theorem says it is not possible. However you direct the edges, however you orient the edges, there will always be a path of length, directed path of length chi in the graph. So, today we are going to do the proof of this thing. So, this is the way. So, we consider a directed graph D. Now, the directions, so what we first do is, suppose this is the directed graph, we start taking some edges from it in such a way that there are no cycles in it. So, we will keep adding edges as long as we do not introduce. So, we are picking up a subgraph D dash of D with the following property. There are no directed cycles in D dash, and also this is a maximal structure with respect to that property. That means, we keep adding as many edges as possible from D. We are taking the edges from D and making D dash, but we keep taking as many edges from D as possible, as long as we do not introduce a directed cycle in D dash. This is a maximal acyclic subgraph of D, that is D dash. So, this is the maximal acyclic subgraph of D. Now, so the point is, we are going to show that. So, there is a we know that suppose the chromatic number of D is equal to K. Now, any valid coloring of D should have at least K colors, right. Any valid coloring of D dash should have at least K colors, that is what it means. Now, what we are going to do is to show that there exists a path of length K in int. So, this is the way we are going to do. Instead of showing that there exists a directed path in D, we would show that there exists a direct path of length K in D dash, in this subgraph D dash, maximal acyclic subgraph of D, namely D dash itself, right. This is what my plan is. So, we pick up this D dash first. Now, we will color the vertices of each vertex as follows. Give a color. What is the strategy? Starting, say for instance, if this is U, we will see which is the longest directed path going out of U. So, this is what, suppose, so among this is a directed path going out of this was one, this was another one, right. So, but then the longest one, if you look, it is this, right, this one, this one, this one, this one, right. So, and then that how many vertices are there in that path, that we will give to, that will be the color of U, that will be the color of U, right, that will be the color of U. Now, now what we are going to do is we will say that, so every vertex got a color, we will claim that the colors that we have given to each vertex will define a proper coloring of this graph D, directed graph D, which means that the number of colors used should be at least K. If it is a proper coloring, the number of colors used should be at least K. That means there should be one vertex which got the value K or more, right. So, which essentially means that if you look at the longest directed path starting from there, it will have at least K vertices in it, right. That is what it means, right, because our coloring strategy was to consider the longest path starting from there and then give the value of the color as the number of vertices in that path, right, to that vertex. Now, the point is, if it is a valid coloring, there should be one vertex with color K or more. Therefore, the path which is starting from here, the longest path which is starting from here, that vertex should be at least K, that is the path we are looking for. So, now how do you show that this is indeed a valid coloring? So, we can consider each edge of D and show that the endpoints of each such edge has to be colored differently. So, now suppose there are two cases. So, consider an edge of D. Now, in this edge in D may be an edge in D dash or may not be an edge in D dash. Suppose it is an edge in D dash. So, we will consider this edge x y. Suppose it is an edge in D dash. Now, what is the color of y? So, the y is, because the color of y will correspond to the longest path which is going from the longest path which is going from starting from y, the longest direct path at d dash. Is it possible that this red one will come and hit this red path, that is the longest path which is going out of longest path which is going out of the longest path which is going out of y, starting from y, will it come back and hit x once again? Will it come back and hit x once again? Is it possible? This is the question, right. So, this, if this can come back and hit x once again, and then we know that. So, if you start from y, this comes here and x y is an edge, it will form a directed cycle. We know that in d dash there is no directed cycle. So, therefore, this red path cannot hit here because x y is also an edge of the d dash. So, this will never happen. So, it will go somewhere else only. So, this will never happen. So, it means that so you can, when you consider the longest directed path starting from x, you can first go to y and then follow the y's longest path. So, it will not be a cycle at all, it will be longest directed path. So, therefore, the value that x gets, the color value that x gets will be at least one more than the color value that y gets. This is what we can. So, the color of x will not be equal to color of y is what we can infer from this. Now, the next situation is, suppose this edge x y in D, the edge x y in D was not an edge in D dash. In D dash that edge is not there, but what will happen if I add this edge x y to D dash? Then immediately a cycle will form. Why? Because D dash was selected as a maximal cyclic subgraph of D. Therefore, when you add x y, so there should be a directed cycle in D. So, which means that, so there should be in D dash there should be a, in D dash there should be a directed path, in D dash there should be a directed path going like this and somehow reaching here, right. It should be possible to start from y and reach x like this. This is what we know, right. So, now let us see that yeah, so this directed path is definitely there, and so such that if x y is added to D dash, then this cycle will come, that is why x y is outside. And now we see, if you look at the color of x, it will be actually the length of the longest directed path in D dash starting from x, something like this. Now, the question is it possible to go and hit y somehow? Is it possible to include in this path starting from x, the longest path starting from x, can we have y? It is not possible, because if it is there, then we can always travel like this starting from x through the green edges and through these black edges, and then we can come back here to x, forming a directed cycle. So, this will never happen. So, this portion will never happen, right. So, this will never happen. Now, what we see is the color of x corresponds to the length of this path, right, length of this path. Now, color of y will be more than this, because there is a path going like this and then following this path, right. This path y to x black path and x to the path which is starting from x, the green one which I have, together there will be more than that. So, we see that the color that y gets will be greater than the color that x gets. So, in both cases, whether an edge of D is in D dash or not in D dash, the color of x has to be different from the color of y. So, therefore, it follows that this coloring strategy correspond to a proper coloring, gives a proper coloring for the vertices of D, and now we can say that because it is a proper coloring, number of colors used is at least k. So, there should be a vertex which got the color value k, and now that means that there exists a directed path in D dash with k vertices in it. So, that is what Gallai-Roy theorem proves. The chromatic number of the graph is a directed graph is k, then there should be a directed path of length, that means of vertices, number of vertices k in it. So, this we have proved now. So, it means that in directed graphs also the chromatic number can tell us something about the structure of the graph. Now, in this class, so before leaving this topic of coloring, we would look at some other coloring problems just for a quick overview. So, we will look at some other interesting coloring problems and some important questions in that. So, here is another version of the coloring problem, so which is called the Cyclic H, Acyclic coloring problem. What do we mean by a cyclic coloring problem? It is indeed we are seeking a proper coloring of the vertices as usual, but with an extra property, namely we want to color the vertices of the graph such that there are no bichromatic cycle in it. For instance, if you look at two colors, say black and red, we should not see a cycle of this sort. So, finally, when you pick up the black vertices, say, and the red vertices along, so together we should not see any structure of this sort, say this sort, right, sorry. So, we should not see any structure of this sort, here black, red, black, red, black, red, a cycle. So, in other words, if you look at the vertices, the black and red vertices alone, what the structure should be just forest. That means, so it can be something like this, right. So, forest, no cycles should be formed. So, this, so of course, this connection won't be there, sorry. Yeah, so forest is only allowed. So, no bichromatic cycles are allowed, or in other words, if you examine any cycle, there should be at least 3 colors in it. At least if you look at the colors or the vertices participating in any cycle, there should be at least 3 different colors. This is what it says. So, now the question is how many colors are required to achieve such a coloring. The minimum number of colors required to achieve such a coloring is called the cyclic chromatic number of the graph. So, it is also denoted as a dash of g. So, let us also discuss different variation of the so an edge version of the problem, which is a cyclic edge coloring. The question is to color the edges of the graph such that, of course, we want the coloring to be proper as usual. That means, two adjacent edges should not get the same color, and we should again we have also this condition that there are no bichromatic cycles. The minimum number of colors required to achieve such a coloring is known as the cyclic chromatic index. Minimum number of colors required to achieve such a coloring is known as the cyclic chromatic index a dash of g. This is what the cyclic chromatic index a dash of g. So, when it comes to a cyclic edge coloring, we know that a cyclic edge coloring has to be proper, right. So, because it has to be proper. So, like the proper coloring, the lower bound of the maximum degree is valid for the cyclic chromatic index also. see delta, we know that delta is less than equal to chi dash of g, namely to proper, if there is a vertex of degree delta, then all the edges incident on that vertex has to get different colors. So, the delta colors are required even to proper color, and acyclic edge coloring has to be definitely it has to be a proper coloring. So, it has to be at least more than that, right, but how much more? We have learned that Wissing's theorem says this number, right, is at most delta plus 1. We can color the edges of the graph in such a way that there are no bichromatic cycle using at most delta plus 1 colors, but delta plus 1 colors are sufficient. But for acyclic coloring, it may not be necessary, sometimes may not be enough, sometimes you may need more. So, you can show some examples where it needs more, but we will show that. But see, but there is a famous conjecture called Acyclic H coloring conjecture by Allen, Sudakov and Sachs also, and this conjecture was also proposed by a Russian scientist called Fiamsik before Allen, Sudakov and Sachs, and they conjecture that the acyclic chromatic index is at most delta plus 2. It is indeed a strong statement. That means the requirement of a cyclicity that no two colors should form cycles, no or any cycle should not contain less than 3 colors. I mean, there should not be a cycle using only 2 colors. That will not increase the requirement on coloring by too much, that is only delta plus 2 colors are enough. This is what they are saying, right. So, now there is a question of case, is delta plus 2 colors are required or not. So, or even is it possible that there are some graphs which require delta plus 1 colors. Okay, that we know, even in proper coloring delta plus 1 colors are required. So, now for in particular we can show that if a graph is k regular, say let us say delta regular, because we will use the same term because the maximum degree is same as all equal, the degree is equal for all the vertices, therefore, we can say delta regular. Now, we will show that delta plus 1 colors are required, Why is it so? This property is somewhat different from the proper coloring, because we know there are there are k regular graphs which can be proper colored using just k colors, k regular k colors. It is not that every k regular graph requires k plus 1 colors for its proper coloring, but then when it comes to acyclic coloring, we need k plus 1 colors. Why is it so? Because so you just start from one vertex, because there are its degrees k, or so k's. Now, you know, all the, because only if you are using only delta colors, then all the colors should be present here. It should be something like this, all the colors should be present here, right. So, yeah, it should be the edges, all the edges should be different, and all the, so this we know by properness requirement, this should be distinct is same, correct, but then if we are using only k colors, then all the k colors have appeared here, not even one color is missing here. Now, we can pick up 2 of the colors, say as our favorite colors are red and green. So, it is that we can travel by the green edge, say we reach here. Now, in this vertex also, if I search, I will find a red color, because all the colors are present there, right, because only k colors are there. and then all the k edges around them should get different colors. So, red color should be present, we can follow the red color, and now here we will find out the green color will be there. Now, here we can find out the red color and so on. So, how long can you go like this? So, always you can go forward by red green red green red green. So, now where will you, how will you stop, because the graph is finite and it has to stop somewhere. The only way is to form cycles. So, you come back here and then you have to enter through this red edge here, right. So, that means there should be a red green cycle. So, any two colors if you take, we should get a cycle of using those two colors, two type of colors. So, right, red and green. So, therefore, it is not possible to have just k colors, because if just k colors are, this problem comes. So, we should have at least k plus 1 color. Why? Because if there are k plus 1 colors, in some point it is possible that we may not see the outgoing green edge or outgoing red edge. So, therefore, we may have to stop there. This sequence will not continue, like at some point it may break even without coming back to the same vertex. So, that is why it needs k plus 1 colors. Now, we claim the next point is that is it possible that so every graph can be colored with delta plus 1 colors. Why delta plus 2? Why the conjecture? So, then this is the reason. In fact, there are a lot of graphs which require delta plus 2 colors. In fact, there are a large number of them. So, the following statement can be made. In fact, suppose G is a graph with 2n vertices, then if G is a k regular graph with k greater than n, then a dash of G is greater than or equal to k plus 2, that is delta of G plus 2, right. This is what we can tell. So, that means the degree is, so I am considering graphs of even number of vertices. If the degree is strictly more than n, then the cyclic chromatic index has to be greater than or equal to k plus 2. Why is it so? So, this is the reason for that. Now, you consider a color class. Color class means you can consider the edges colored red. Say suppose these are the edges colored red, right. Suppose I am assuming that suppose there is a coloring using k plus 1 colors. Now, you pick up the red edges alone. Now, you consider, suppose this happens to be n edges. So, there are 2n vertices. Can you have more than n edges? No, it is not possible, because so it has to be a matching, right. Then the color class should give us a, because they do not touch each other, because it is a proper coloring. Now, the biggest matching possible for 2n vertices is only n. Suppose you get one of the color class to be of cardinality n. Now, is it possible to have another color class, say green color class, also to be of cardinality n? Suppose it is also of cardinality n, that means the green color class also defines a perfect matching. That means every vertex is touched by a green edge also, like the red edge touches every vertex, some green edge also touches every vertex, like this, right. You will always be able to find out both red and green at every vertex, right. Now, what will you do? So, now we see that, like in the earlier argument, we see that we can start from this vertex, we follow the red edge here, right, follow the red edge here, we follow the red edge here, yeah, the red edge here. Now we follow the green edge. Right. Now here this vertex also will have a red edge because it's a red is also a perfect matching. Now we can follow the green edge from here because green is a perfect matching, and then we can follow the red edge. So this will, where will it stop? This again the question. Because it cannot keep going, right, till, because the graph is finite, it has to end somewhere. The only way of ending is to come back and join with one of the earlier things like this. So this will give you a red green cycle. So that is a contradiction because we are saying that it is an acyclic edge coloring, and there should not be a cycle with just two colors. Here is a red green cycle, that will not happen, that cannot happen. So therefore, which means that there can only be one perfect matching, if at all there can only be one perfect matching. The red can be a perfect matching, then no, green cannot be a perfect matching, blue cannot be a perfect matching, no other color can define a perfect matching. So one of the color class can have n vertices, one of the color class can have n vertices, n edges in it, n edges. The remainings at most n minus 1 edges are possible in remaining. So total number of edges can only be n plus, there are k plus 1, right, k into n minus 1, right. How much is this? So this is kn in plus n minus k. This many edges are the maximum you can get if there are only k plus one color class and k other color class. So now you see that this thing will be, suppose we have assumed that k is strictly greater than n, this would imply what? So this n minus k will be a negative number. So this together will be strictly less than kn. So how can it be strictly less than kn? So if every edge is colored, together if I sum up the color classes, the cardinalities of the color classes, it should give the total number of edges, right. And how many edges are there? There are 2n vertices, it is a k regular graph. So 2n into k divided by 2 equal to kn edges should be there. Now we are saying when you summed up the cardinalities of all the color classes, we will get something strictly less than kn, which is a contradiction, which cannot be true. So we can infer that it is not possible to have a coloring using just k plus 1 colors, there should be k plus 2 colors in it. So that is interesting enough, because if the regularity as such tells us that k regularity as such is that we needs k plus 1, but in the case of dense regular graph in the sense is the k becoming greater than half of the vertices, half the number of vertices, then it says that we need k plus 2 colors. It is not just about the regular graphs, one may think that it is something special about the regular graphs. You can, here you can see what we have told is, because when the color classes are added together, we get kn plus n minus k, and if it is strictly less than kn, we have a contradiction. So as long as it is, suppose the difference between this side and this side is x, that means this total, so kn minus this quantity, that is kn plus n minus k is equal to some x. So that means we can remove less than x edges. So x minus 1 edges we can remove from the current k regular graph we are talking about, and still right. So we, that means we can reduce this side by x minus 1, still we will not be reaching the total number of edges by this sum, right. So regularity can be destroyed, but even then we can argue that k plus 1 colors are required, k plus 2 colors are required, making sure that still the maximum degree is k, right. So, that means that some vertex is undisturbed. So, therefore, there are graphs which require delta plus 2, but up to now nobody has found out any graph which require more than delta plus 2. It is possible, but there is this conjecture still open after 20 years. It is conjectured somewhere in 90s, the beginning of 90s. So, it is still open after almost 20 years. So, it is an interesting problem. So, one can try to disprove the conjecture. Now, the next idea is to consider another important problem regarding the chromatic number, the coloring, vertex coloring of graphs. So, this problem is probably one of the most important open problems in graph theory, and this is called the Hadwiger's conjecture. So, this is very important because it tries to generalize the famous 4 color theorem for planar graphs, right. And also several people have already worked on this, and it is known to be a very tough question. So, this is the statement: every k chromatic graph has a k minor. So, we can verify it for small cases, like we can consider a for instance one chromatic graph. So, there is nothing to prove there. One chromatic graph means, so here we have the independent set, right. We have just the independent set. If it is a one chromatic graph, then there is a k1 minor which is there, of course this is a k1 minor. So, there is nothing to prove there. What about two chromatic graphs? So, what can we tell about two chromatic graphs? So, two chromatic graph means bipartite graphs, right. So, in bipartite graphs, is there a k2 minor? Of course there is. So, there is a k2 minor, right. And now what about 3 chromatic graph? So, 3 colorable graph, does it have a k3 minor? So, it is not difficult to see that. So, of course, the k3 chromatic means it cannot be colored with 2 colors. So, they are not trees or forests. So, there is a cycle in it, right, there is a cycle in it. Somewhere there should be a cycle in the graph. It is not an acyclic graph. If it is an acyclic graph, then it should be colorable using just how many colors? Yeah, two colors, right. Now, 3 colors are required. Now, if there is a cycle, then you see that we can contract it and get a k3 minor, right. So, you contract it and you get a k3 minor. So, how do you contract it? You just contract edge by edge and you can convert it to this k3 minor. So, when we say k3 minor, right. So, what do we mean by that? You can throw away some edges, throw away some vertices and contract some edges and ultimately get a k3 complete graph on 3 vertices, a minor. Now, the next question is it possible that there is a 4 chromatic graph? Is it so? Sorry, if you are given a 4 chromatic graph, there is always a k4 minor or not. So, this is also true, because what we can do is, if you take a 4 chromatic graph. So, we consider the critical graph of that color critical 4 color critical subgraph of the given graph. There is always one, right, as we have already discussed. And one property of this thing is it is already the minimum degree is already 3. So, there is a we can easily show that it is not a it has a k4 minor. So, there is a result of Dirac saying that the graph which because the minimum degree is already 3, there is a K4 minor. The graphs which does not have a K4 minor are the so called series parallel graphs. So, what is a series parallel graph? So, it is a special kind of planar graph which is constructed like this. So, you can say this is a series parallel graph, this edge is also a series parallel graph. Then starting from these basic things, we allow 3 kind of operations. One is add a pendant vertex, this is one operation which is allowed. For instance, if this is a series parallel graph, so we can add this is also a series parallel graph, this is also so the trees are all series parallel graphs. You can, if you already got a series parallel graph here, you can add a new vertex like this, pendant vertex, that is allowed. Then 2 is that you can suppose there is a edge here, so you can add a parallel edge, which means you can add an edge like this or like this, how many ever you want, right. This is the parallel edges. So, if there is an already existing edge, you can add a edge parallel to it. So, of course, one can see that this defines a multi-graph, not necessarily a simple graph, sometimes it can be a multi-graph. So, parallel edge addition is allowed. And the third property is that you can do a series operation, What do we mean by series operation? Series operation means, suppose you have a edge here, say essentially series operation means it is a subdivision operation. That means you can break this edge and introduce a new vertex here. So instead of this one edge, you put a path of length 2, right. You can keep on doing that once. So this is a series operation. So you start with one vertex and keep on doing any of these given operations, the pendant vertex addition or parallel edge addition, or doing a subdivision operation, it's called series operation. So whatever graph you can create like this is called a series parallel graph. You can easily see that, right. So this finally the series parallel graphs minimum degree has to be 2. It is a 2 degenerate graph, means there is a sequence. For instance, if you look at the backward sequence, I mean the way you create it, the reverse sequence, if you look, you see that every time you are introducing a new vertex, so that is only a single degree. So when it comes to a simple graph, I mean, so the parallel edges without counting the parallel edges. So usually typically what we do is we create a parallel edge and then break it by a series operation, right. So this are always going to be a 2 degree vertices. So they are 2 degenerate graphs. So they can never be 3 regular graphs. So the Dirac proved that these graphs does not have K4 minus, and these are the only graphs which does not have K4 minus. And so therefore anyway, so we can, using Dirac's theorem, we can show that a K4 chromatic graph does not have has a K4 minor. Now the case of 5 chromatic graphs essentially is much more difficult, because 5 chromatic graph means if 5 chromatic graphs have a K5 minor, if you can easily prove that, then it means that the planar 4 color theorem can be easily proved. Why? Because no planar graph can have a K5 minor as we have seen, because the operations involved in constructing minors preserve planarity. Like you can remove an edge, remove a vertex without losing planarity, and also you can contract an edge without losing planarity. Therefore, if you say that a K5 is a minor of a graph, because K5 is not a planar graph, the original graph also cannot be a planar graph, because when you keep on doing these operations the planarity is preserved. You cannot reach a non-planar graph by doing these things. So, we get that any planar graph has cannot have a K5 minor. So, if it means that, so the suppose there is a planar graph, which requires 5 colors, that means it is a 5 chromatic graph. So, if this theorem is true, it is like telling that any 5 chromatic graph has a K5 minor, that such a planar graph which requires 5 colors to color it has a K5 minor, which will be a contradiction, which will not be true, right. So, what can we infer from that? We can infer that no planar graph can be can require 5 colors, all planar graph can be colored using 4 colors, that is the immediate inference, right. So, this statement for the chromatic number equal to 5 case will immediately imply the planar 4 color theorem. So, therefore, proving it will not be so easy. So, because we know that the planar 4 color theorem was a very difficult question, and it took almost 100 years to come up with a solution, that too not very elegant with a lot of computer assistance. So, we have already discussed it before. So, this so we can only hope probably to use the 4 color theorem to prove the case, the Hadwiger's conjecture, this that is all 5 colorable graphs have a K5 minor. So, sorry, all graphs whose chromatic number is 5 has a K5 minor using the planar graph theorem. So, of course, the Wagner has achieved that. Wagner has shown that if you consider the edge maximal graphs, so the then which are those graphs which requires 5 colors, 5 chromatic graphs, they can be either planar graphs or some very special classes of graphs which I have shown to be 5 which sorry the graphs which does not have a K5 minor. So, and you take the maximal graphs, then he has shown that there are only 2 categories, and then they are always 5 colorable. So, so of course, they are 4 colorable. So, that this case was considered by Wagner, and he has come up with a convincing argument. Okay, of course, using making use of the fact that planar graphs are 4 colorable. Now, the next case was proved by Robertson and Seymour. So, that is the 6 color, which was also using the planar 4 color theorem for its using 4 color theorem, planar 4 color theorem. They relied on that, and then the later from there on the problem is still open. For instance, K7 onwards it is still open. So, that remains to be one of the major open problems in graph theory even now. So, and when we discuss Hadwiger's conjecture, it is very natural to remember historically there was another conjecture called Hadwiger's conjecture, which was a stronger conjecture, and it told every K chromatic graph has a subdivision of Kk. That means, the Hadwiger conjecture only claims that every K chromatic graph has a Kk minor. Here it is a stronger requirement. It says that there is a topological minor of Kk. So, but unfortunately, this conjecture is not true, and it was disproved by Catlin. He showed a kind of graph which is K chromatic, but does not have a subdivision of Kk. and in fact it can be shown that with some using some of the models, probabilistic models which we haven't yet discussed, that almost all graphs will be a counterexample to Hadwiger's conjecture. So, that is the story about the two important conjectures in the graph coloring theory, Hadwiger's conjecture. So, that Hadwiger's conjecture was disproved, end of case. So, then nowadays so many counterexamples are known for Hadwiger's conjecture. Now, the next our plan is to discuss some. These are the main conjectures about the vertex coloring. Another thing is, of course, why the coloring, how this coloring idea, the vertex coloring idea, chromatic number, this concept can be generalized. So, for instance, one possible way is to define something called a homomorphism. So, I am just telling it for the sake of looking at various ways in which people have tried to generalize it. This is one interesting possibility. So, here here you can have a graph G. So, here is a graph G, and now from the vertex set of G you can define a function to a smaller graph, say H to H, V of H we can say, right, such that suppose there is an edge here between U and V, right, then the corresponding edge should be there in between f of u and f of v, right. So, this is a homomorphism, right. So, see for instance our suppose if H is a complete graph, suppose H is a complete graph, then you see the for each vertex the pre-images of each vertex will form a color class, right. So, then because between right, so this will be a coloring, because between whenever there is an edge here, the corresponding, whenever there is an edge here, then there should be a corresponding edge here also, right. So, therefore, this will correspond to a coloring, and now suppose H is not a complete graph, it will give a slightly different notion of the coloring. So, that is an interesting kind of generalization which one may want to read up. So, then the next topic we are going to study is the perfect graphs. So, in the next class we will consider this thing. So, this is essentially again a topic in graph coloring in some sense, because the definition of the perfect graphs is related to the concept of coloring, but still it essentially it is a very interesting class of graphs with a lot more properties, and there are several subclasses of perfect graphs which is practically useful and theoretically interesting. So, we get a chance to study all those things. So, that will be the next topic. So, in the next class we will discuss about that. Thank you.